right, good evening, everyone, and thank you for coming to our February After Hours. My name is Candace Vincent, and I'm the Outreach and Events Coordinator here at the Virginia Institute of Marine Science. The lecture tonight will be given by Emily Hein, Assistant Director for Advisory Services here at VIMS. Emily Hein earned her Bachelor of Arts in Earth Sciences from Boston University and her Master's of Science in Geology and Geophysics from the MIT Woods Hole Oceanographic Institution Joint Program. After obtaining her degrees, Emily combined her love of sailing with her passion for science and worked as the Technical Science Coordinator for the Sea Education Association, working with students and scientists on shore and at sea on the program's two tall ships. Emily joined the Office of Research and Advisory Services at VIMS in 2013. And for those of you who regularly come to After Hours, you know I like to ask our presenters a fun fact about themselves. And Emily's fun fact is that in 5th grade, she was voted most likely to become a scientist. So fulfilling her childhood dreams, here's Emily Hein.
Well, good evening. So how many of you have driven across one of our 3 bridge tunnels? Excellent. Maybe getting stuck in traffic, at least in the Hampton Roads Bridge Tunnel, the HRBT. The one on the screen here is the Chesapeake Bay Bridge Tunnel. And I'm going to talk a little bit more about the Hampton Roads Bridge Tunnel and all of its traffic. You may have seen recently driving across it that there's rather a lot of construction happening. And that is all part of the very large Hampton Roads Bridge Tunnel expansion project, which will include 2 new tunnels and widen approach bridges and a rather large project. And so I wanted to go into a little bit of the details of where that project stands right now. And it is such a large project spatially that the best way to do that is looking at satellite photos. So I'll walk you through the changes here. It's a little bit hard to see, I know. The photo over here is from April of 2020, before any construction on this project started. And over on this side, we have one from earlier this month. So one of the first changes you see is these moorings and work barges. And then there is the south approach to the tunnel, new bridge being built. If you look closely, you can actually see a very small little road between the 2 existing bridges. That actually is a maintenance of traffic trestle that opened on Sunday. So you get to drive across that now, so that, you know, traffic is maintained at its current awful state during construction instead of getting even worse. One of the most noticeable changes is that the North Portal Island has more than doubled in size. And then the north approach bridges are also being are under construction. And if it were summer, say in July of 2022, you would see these 3 barges anchored between the South Portal Island and Rip Rap Island, which have nesting substrate for migratory birds on them. It's for those migratory birds that were displaced from the South Island during construction. And just to get a little better view of those, I'm standing on Rip Rap Island looking out at those bird barges a couple of summers ago, happily in August, so I didn't have to wear my raincoat because most of the birds had already migrated at that point. So all of this construction, there is a lot going on all at once. This is a really big project. Why am I telling you about it? If you ever considered the environmental impacts of a project like this. So it's such a big project. It's in the marine environment. We're here crossing the mouth of Hampton Roads on a very large scale. And looking at impacts, marine environmental impacts of a project like this, and ways to reduce them and mitigate for them is what I do. So many other colleges, universities, their missions are research and education, as is ours, except we're unique in the fact that 1/3 of our mission is advisory service. So by law, we are the marine science advisors to the state of Virginia. And so what does that mean? We use all of the science that happens every day at VIMS to answer questions and evaluate proposed projects and legislation, anywhere from any tidal areas to subaqueous and off into the shelf. And so, for example, this figure here shows all of the regulatory agencies that have, a piece of the action on a shoreline, regulate different parts of the environment. Now at VIMS, we don't have any regulatory authority, but we advise those who do. So for example, if VMRC, the Marine Resources Commission, wanted to ask us questions about a project that impacted subaqueous lands, then they could do so and come to us. Or in the intertidal between mean low water and mean high water, a local wetlands board might ask us a question. So we do this all over the state. So anywhere that is tidal. So this image shows probably an underestimate of the project requests, review requests we've gotten over the last 3 years. Each color is just a different fiscal year, and the dot sizes correlate to estimated project costs. And so you see, anywhere that's tidal, we go all the way up in the tidal freshwaters up to Alexandria and Fairfax, down to Richmond, Chincoteague, and Virginia Beach. Anywhere that's tidal, you see all these dots. So I can't show you all of these projects. It's a lot. So I'm going to take you on a tour of 4 project review requests that I've participated in over the last few years, and then add on a couple extra, a little bit different fun things at the end as well. So our little peg man is in right where we are now in Gloucester Point. And so if we go back to traffic on the HRBT and show you how we approach looking at a project. So the Hampton Roads Bridge Tunnel expansion project is huge. And so I wanted to start off with this project because it's a great example of sort of showing all of the possible things we could look at all in one project. And so one of the first things we were concerned about with the HRBT project was if it was going to be an open cut immersed tube tunnel project. So all the current bridge tunnels, the tunnel part of them, were built that way. So you dig a trench, lay the pipe in through the water column, bury it back over, pump all the water out. And so doing that has some larger environmental consequences, digging around, dredging, and reburying all of that. So this bridge tunnel is being built with a tunnel boring machine named Mary. This is Mary. She was built overseas. She is now being reassembled in Hampton Roads. And so all those impacts we don't have to worry about right off the bat. It was great. We did look at hydrodynamics and water quality, submerged aquatic vegetation, shellfish, finfish, wetlands, wastewater discharge, and I'll tell you a little bit about those. So one of the very first things we looked at was hydrodynamics. Now, hydrodynamics are just how water moves and interacts with things in its path. And in very small letters, you might notice that the figure year is 2016. So well before the bridge tunnel application was put in, VIMS scientists were contracted to do very high resolution 3-dimensional modeling for what hydrodynamic consequences there might be to adding the new bridge tunnel, which is really the bridges were the concern. And also at the same time, we were looking into expanding the Port of Virginia. so deepening and widening a lot of the dredged areas. And so you're concerned that those might have a cumulative impact that could really cause some problems. So they were both modeled at the same time to be able to do sort of a worst case scenario all at once. And that modeling, I listed some of the things that it included. It could be a whole lecture or more going into just that hydrodynamic modeling. But the main conclusion is that there aren't big problems. And as an example, the change in salinity was less than 1% at its highest location, very close to the north part of the bridge. So we were not concerned about hydrodynamic impacts. We also looked at submerged aquatic vegetation, also known as SAV. So SAV is a very high value ecological resource, both for habitat, for nursery habitat, for juvenile and larval fishes and blue crabs and clams. And it is such a high value resource that the Chesapeake Bay Watershed Agreement uses SAV area as a water quality proxy in the bay. So SAV can only grow in clean, clear water. And so each bay segment actually has a restoration goal of number of acres in each segment. So we want to impact that as least as possible. And for the HRBT, there is a nice big persistent SAV bed on the Hampton shore. And the project was going to impact about half an acre. And just for context, we're usually measuring SAV impacts in square feet. So that was a concern, but then we realized that those impacts were mostly temporary structures. So those are maintenance of traffic trestles and construction trestles that would be in place for most of the 5 years of construction, but then removed. So that gave us the opportunity to recommend restoration of an area that previously was an SAV bed, was impacted for a few years. We know it's great habitat. It's perfect. It's a great garden bed for it. We know it grew well there. And so we recommended that area be restored after the construction was complete. We looked at shellfish. So VIMS scientists were also contracted to look at shellfish in the project area, and they found very few. And the species that had the most animals in the area were hard clams, which is what's pictured here. And there were very few of them, and the habitat was very poor. So we did not recommend that there was mitigation needed for hard clams. There are vegetated tidal wetlands impacts. Now, most of those are temporary, again, for construction access. So a lot of that looks like what's depicted here of a construction matting in a wetland so that large equipment don't sink. And so for those temporary situations, we recommend that they're restored. So the elevations are all restored and planted as needed after construction is complete. And for those impacts that are permanent, then the applicant purchased credits at a wetlands bank that was in the same watershed. So lastly, we looked at finfish. Now, this is a very large area of water. So as you might expect, there are a lot of finfish around. And we have a very long running survey called the VIMS Juvenile Trawl Survey that has 4 survey locations within the vicinity of the project. So we were able to very accurately detail, we know what's around this project. And in the 10 years prior to the application submittal, there were 79 different species, with 22 of them managed by various agencies. And those are both resident species that spend their full lives in the area, like these spot in the top photo, and anadromous species, which live their lives in the ocean and then come back to their natal freshwater streams and rivers to spawn. and like this striped bass in the bottom photo. And so we were concerned about all of those fishes. And one of the things we were most concerned about is noise from hollow steel pile driving. There are a lot of hollow steel piles being used in this project. Anything that's temporary, they use a hollow steel pile for. So hollow steel piles are a little bit different than other materials like driving a wood or a concrete pile, because when you take a tube of hollow steel and you hit a hammer on the top of it, that noise reverberates and rings on the inside to create a sound wave that is loud enough that actually can kill some fish, specifically those with swim bladders, like our striped bass friend. Or if you're farther away, it might just kind of stun you and not make you feel good. Sort of like if you've been to a rock concert, you leave, and you realize, oh shoot, my hearing's a little bit funky, hopefully not for very long. But during that time when your hearing's a little bit off, I bet somebody could come sneak up behind you and tap you on the shoulder and scare you pretty easily. So if you're a fish and that happens, the somebody coming up behind you is probably going to make you dinner. And so, even if the sound itself isn't causing mortality directly in the fish, it definitely increases the potential for sort of secondary mortality by being eaten when you're a little confused. So we are concerned about the impact of that hollow steel pile driving on fishes. And so we made recommendations for a time of year restriction to restrict when that pile driving could occur, to have it be outside of the time of year when the anadromous fish that are migrating through the area are nearby. And then also mitigated measures during pile driving, which would include cushion blocks, so a block of wood on top of that piling to help dampen that sound. A soft start technique, which is basically you start pounding on that piling, not at full force, wait a few minutes, start pounding a little harder, wait a few minutes, try to scare the fish away from the area. And then also bubble curtains. So bubble curtains I've depicted here. This image is actually from an offshore wind turbine being installed in Europe. The same principles that you have. This is a jack-up platform driving a hollow steel pile in the middle. And you can see the white ring here is the bubbles coming up to the surface. So below the surface, you have that hollow steel pile in the middle here. And then the ring around it is a hollow tube with lots of little holes in it, with compressed air being forced through it, so that all those bubbles go through the holes, creating a bubble curtain around your piling, and those bubbles disrupt that sound wave, and therefore are protective of a lot of the fishes around it. So those were our recommendations. And these were a lot. These were the ones that we included in the first of our formal recommendations for the project. And so I wanted to give you a little bit of a sense of everything that we have to go through from a paperwork standpoint. So these are screenshots of the VMRC tracking database of all of the documents for this permit, or well, the first page of them. And this is only, if you look at the top, from September of 2019, when the first version of the permit was submitted. So I personally started working on this project before it became the Hampton Roads Bridge Tunnel Expansion Project, back when it was the Hampton Roads Crossing Study, when we didn't know what we were going to do, if we were going to have a third bridge or whatnot. And so that was in 2014, and others at VIMS had been working on this project long before that. And so lots went on before we even got to this point. And so please don't read these. Each line is a different either part of the application or a revision to the application, or a different, impact revision, comments from other agencies. So we have, comments from the local wetlands board, comments from the department at that point, but still the Department of Conservation and Recreation, NOAA Fisheries, the Army Corps of Engineers, and us. So these are just our formal comments, not those given at meetings or phone calls or anything. These are our formal written comments. And so, but this isn't it. Going to a second page. We ended up commenting 4 times formally on this project. And again, that's just the formal ones. And of note, you see line 136 here is the permit document. And it keeps going, because anytime there's a revision that changes impacts or changes construction means and methods, that has to be okayed by the permitting agencies. And you'll note even that the last number here, 224, was just uploaded earlier this month. And that referred to this permit modification ahead of it that I was on the phone giving informal comments to VMRC on that week, because this project isn't finished, and it's so large that I expect this list to continue into the future. Be curious if anyone wanted to take bets on how many lines it would go on. But so as we're giving all these comments and trying to give our scientific advice, again, we don't have any regulatory authority. We're just giving advice. So I wanted to share how that's taken. So again, you don't need to read this document. This is the final 2 pages of the permit itself. And so every permit that VMRC issues has permit conditions at the end. And there's a standard suite of permit conditions, like this must be posted prominently, outside your work site. You have to notify VMRC if when you start work, you have to, do that sort of thing. After those standard conditions, there are special conditions. And so those special conditions that are results of our input, these 4 are about hollow steel pile driving. Now, they didn't take all of the suggestions that we gave, because the commission has to weigh everything. They have to weigh the length of time the project is going to take on such a large project, the cost, all of that, including one part of it is our scientific advice that they have to weigh. So while they didn't take all of our suggestions for hollow steel pile driving, for example, there are still 4 conditions that relate to it from what we had suggested. These 2 relate to fish passage and habitat. This one's about submerged aquatic vegetation restoration. This one's about beneficial use of sandy dredge material. So, again, we don't have regulatory authority ourselves. However, those regulators, do take our comments and our suggestions into consideration, and often, one way or another, are incorporating our information to some degree. So I think we've sat in traffic long enough, and we should go across the other bridge tunnel and head to the eastern shore and look at a project on Savage Neck. And this is an interesting project because it was built in 2009. So we get to see how it was done. So how it's done since then. So this is a shoreline on the bay side of the eastern shore. So it's a beach open to the whole bay width and all of the large waves, that long fetch. And the project was to build 3 stone breakwaters to protect this eroding shoreline, which is the appropriate sort of strategy that we would recommend in this case. So it was before I got to VIMS when this was in its application phase, and we got brought in because south of this property here and farther south is the Savage Neck Natural Area, which is a state-owned preserve where there are an abundance of federally endangered Northeast Beach tiger beetles. And so they were concerned that these breakwaters being installed and functioning as they were designed to would impact the beach where these tiger beetles nest. So to talk a little bit about breakwaters, we have to talk a little bit about physics, which I couldn't resist. So breakwaters are, they're a large pile of rocks in the water, right? And so very simply, they act as a wave break. A wave hits them and it's a speed bump, it slows it down, it breaks on there instead of the shore. That is only a piece of what they do. More complicated, they act as a multi-slit diffraction grid. So if you have a wave that hits these breakwaters, you can see here you have waves coming perpendicular to the breakwaters. They come in through the slits and then diffract around. And you can see that in this aerial view, you can actually see the wave crests diffracting around, and as they interact with each other from each side, you are concentrating that sand that the waves are carrying behind the breakwater in the middle. And so a feature like this, where the shoreline isn't connected to the breakwaters, we refer to them as salients, and more common around here, at least, if this sand connects all the way to the breakwater, we refer to that as a tombolo. So you may have thought about these or interacted with these, like if you're back in middle school or high school, science class, and you have a card with slits on it, shine a flashlight through it, right? See how the light acts as waves and interacts with each other. And so the breakwater is the exact same thing. It's just instead of light acting as a wave, it is water acting as a wave going through these slits. But waves don't usually hit the shore directly perpendicular to it. So most waves hit the shore at an angle. And that angle is, there's usually a dominant direction of wind and therefore waves in a location. And so as those waves hit the shore at an angle, it crash at that angle, and then gravity brings them back down. Crash at an angle, gravity brings it back down, right? And so your net movement is along shore instead of just on and off. And so your wave is moving along shore, and the sand or sediment that's being carried by those waves are also being moved along shore. If you've ever been to the beach, particularly on the ocean front where you actually have some larger waves and you've been out in the water for a while and you go to take a break, go get out of the water, back on the beach, you've noticed that you're suddenly far down from where your towel was. You are the particle that was being moved down current by those waves. So we combine that longshore current with our breakwaters in the real world and come up with a design like this. So this image, aside from the color, is taken directly from the permit application for this site. So I wanted you to see a little bit of the type of drawings that we evaluate, that we get, these engineered drawings. And this is a very good one with lots of information. And so here in the top, where we're looking at a plan view, this red line here that I've drawn in is mean high water. The purple structures are the breakwaters. And you can see the same thing in the lower cross section. So the purple rock breakwater, that red line is mean high water. The green is the existing bottom and beach. And then the yellowy orange lines here show the edge of the sand nourishment that is proposed behind the structures. And I will get to this blue bit in a second. So, you know, told you that breakwaters work to trap that sand behind them, right? And so if a structure is going to trap sand from moving along shore, that means that the shoreline farther down current from that is deprived of that sand that's being trapped by the breakwaters. So in order to help mitigate that known and desired consequence of installing breakwaters, we frequently recommend that they are nourished when they're built. So you bring in sand and you artificially create those tombolos that connect the breakwaters to shore, so that you're adding that sand, you're sort of filling up that space right when you're constructing the breakwaters, so that it doesn't trap as much sand going down the shoreline. So with the concerns of the natural area right next to this project, the applicant proposed adding this blue blob, which is a pile of sand. So that, you know, right away, there's a source of sand right there that can be continue to move along shore while the breakwaters are coming into equilibrium and sort of figuring themselves out and trapping sand and, you know, getting all set, which we agreed was a reasonable approach. So let's see how it worked. So this is a picture from 2008, before the breakwaters were constructed, and it's hard to see in this photo. So here is a small house on the shoreline that you can see in all the pictures to keep an eye on and orient yourself. So the next year, we have our breakwaters built. They look exactly like those plans. We have the three structures, the sand nourishment, creating the tombolos behind them, and our pile of sand. And our house is still there. 2010, we've already started trapping sand to the north in front of that northernmost breakwater. And our pile of sand here is basically gone. You can see maybe some remnants of it moving down current. A couple years later, we've just continued to really fill up that northernmost breakwater. No evidence really of that sort of bolus of sand left. And maybe we're starting to cut in a little bit here to the south. 2014, more of the same, lots of sand being trapped by that northern breakwater. 2016, there's a lot more sand now, has worked its way down to the next gap in filling in between the northern two breakwaters. And we're seeing a bit of erosion here to the south. And again, here's that house. 2018, more of the same. We've started to fill in this last embayment. There's vegetation growing on the high parts of the tombolos. So really showing that there's built up enough sand to have like dune grasses building. There's only a little room between the edge of the beach and that house. And we've cut in here a bit. 2020, you can really see that house is right on the edge. And in fact, the tombolo here where it connects is off center because the waves refracting around here, the end is really causing that to curve, a nice curved embayment there. And 2021, we are really full of sediment. These breakwaters are working exactly as designed. They're doing a very good job at protecting this beach and these houses from continued erosion, except notice our house has moved. So this house got a little too close to the edge, and so actually we were brought back in and asked to give some input on, where the dune was and minimizing impacts of the construction equipment that actually moved that house farther away from the shoreline. And then just to compare where we started just after the breakwaters were built, you can really see how much this has eroded and cut in and really narrowed that beach. And actually, if you go there, there is a public access through the nature preserve, and one of them ends up on the beach, and you should be careful on your tides if you can actually walk along the beach or not, if there is one. So just a little bit better sense where that is. So this is a drone photo I took last summer. I swear that's me right there. And you can see this is the house that has been moved. You can really get a better sense of that eroding bluff. That it's a pretty high bluff, and that house was right here for a while. So I just wanted to show, sort of the progression of a shoreline feature, that these structures behaved exactly as they were designed to, and they functioned very well. And that doesn't mean there aren't impacts from them. And so balancing those impacts and figuring out the best, geometries to design things, and really making sure that, minimizing where we can is something that we look at pretty frequently. So heading from Savage Neck back to Norfolk, we're going to continue looking at some dunes. This is at 11th View Street on the bay side of Willoughby Spit. And if I asked you to picture a dune, what comes to mind? Just picture a dune in your mind. Does it maybe look something like that? You have, nice beach, and then a little, mound of sediment, maybe some grass is growing on it, right? Now, what if I asked you to define that dune legally? It suddenly gets really hard to tell me what a dune is, doesn't it? So this is something that is difficult, defining a natural feature in legal code. So in Virginia, I promise this is the only thing I'm going to read to you. A coastal primary sand dune is a mound of unconsolidated sandy soil, which is contiguous to mean high water, whose landward and lateral limits are marked by a change in grade from 10% or greater to less than 10%, and upon which is growing any of the following species that I didn't list out, but are in yellow over there. That's a copy of the actual code section. And VIMS scientists did have some input into the writing of this code section, of this definition, and it is a pretty good definition, a legal definition of a natural feature. But Mother Nature doesn't always play by legal rules, and she isn't always quite so straightforward. So one of the things I do frequently is, at the request of state or local agencies, is I delineate the jurisdiction of dunes. So this example in Norfolk, this graph is taken from the permit application. I'm just going to walk you through the current conditions that I've highlighted in purple. So on this side, we have Chesapeake Bay and the beach, and maybe a little baby dunelet is starting to grow, but here's the dune. We go back down, and then here's a secondary dune, and then over here is the street. So this has been a vacant lot for a number of years, and so when I delineated these dunes, I delineated the first dune here, and then I also delineated the second dune here. Now, I did that because this dune here, the first one, was actually created by the city after a big storm came through and knocked out all the dunes in the area. And so they're trying to build back some resiliency. Get into that a little bit more in a minute. So the proposed project here is to grade down the second dune and augment the seawardmost dune with some more sand and plantings to raise its elevation so that houses could be built in this location here. So what that looks like in plan view, we have Chesapeake Bay at the top, the road at the bottom. And these two lines are those same lines I delineated. And so all these squiggles are contour lines, elevation. And so this is our crest of our seawardmost dune, and this is our crest of our secondary dune. And what's proposed is 3 houses here on that secondary dune and additional ones behind it, but that's not on a dune. So why is that a problem? And why did I delineate that second dune? Well, to continue that same definition, a dune shall not include any mound of sand, sandy soil, or dredged soil deposited by any person for the purpose of temporary storage, beach replenishment, or beach nourishment, nor shall the slopes of any such mound be used to determine the landward or lateral limits of a coastal primary sand dune. So what that has been taken to mean by the State Attorney General's office and DMRC is that if a dune is man-made, a pile, of unconsolidated sandy sediment put there, that dune is not jurisdictional, and you instead go to the next dune back if there is one. So, one reason for that is if you live on the beach and you're not allowed to alter a dune or build on it without a permit, and without following the definitions of this code section. And so if you lived on a beach and you said, hey, you know what, I'm going to make a dune right at mean high water and call that my primary dune so I can mess with this natural one behind it. So you can't do that. And in this situation, where a dune was rebuilt in its original location, but all at once, the same thing applies, because there is a difference between a natural and a created dune. So in this picture here, you can see, so this dune was eroded and scarped during a storm, and you can see these horizontal layers, as well as all these roots sticking out of it, kind of holding that vertical cliff, which sand does not usually like to stay vertical. And so as a natural dune evolves over time, you get a little dunelet, as I like to call them, that builds up, and then vegetation starts growing on it. And then you get some more sediment on top of that, and more vegetation, and more sand on top of that, and more vegetation. And so this builds this complex internal structure that is very resilient and can hold that vertical face and can really provide a pretty strong, barrier line of defense between your house, your property, and the ocean, the open bay. Now, a man-made structure is usually made by piling up sand and planting the top of it. So it doesn't have that internal complicated structure to really hold everything in place and be such a resilient feature. So scientifically, they're different. And so for this project, we recommended that this seawardmost dune not be considered the jurisdictional dune because it was man-made, and instead default back to the secondary dune. In this case, the commission weighed all the information they had, economic benefits, our scientific information, and they decided to grant the permit as it was. So, again, we did our job and gave them the information, they did theirs and considered it with all the other factors. To date, this lot hasn't been built yet, so we don't know yet how it fares. Every time I drive by, it's like, ooh, they started yet. So, maybe in a few years we'll get to step through that one and see how it fares. So going from Norfolk back to the shore, up to Onancock Creek on the bay side, I wanted to show you a smaller project. So this is an individual property owner, single family house, and I have flipped us on our head and north is down, just to orient you. And so this project, so this shoreline here has a bulkhead. It is, this is the side that's more open to the mouth of the creek and the bay. And so this is the side that they are concerned about. You can see, very old remnants of some structure. There's some rubble on the beach, on the shoreline, but there's vegetated tidal wetlands, marshes, a little bit of a beach that you can see is eroding into the upland, and more marsh here. And they're very reasonably trying to protect that property. The wrinkle, and where we came in, is all of this dark colored, again, I think blob is the technical term, is submerged aquatic vegetation. So you remember from our discussion of the HRBT, how important SAV is and how we don't want to impact it. And so this type of project where you have, conflicting resources, you're trying to reduce the impacts to the SAV. You also don't want to impact the marsh, and you want to maintain, successfully have a shoreline control strategy that stops that erosion. So in this case, we were able to, the applicant and agent had already come up with a pretty good plan that we recommended some tweaks to, that they were able to put a little rock sill right along the water to protect the shoreline while also not impacting the SAV. And that is not what we would have recommended had the SAV not been there. So it's a sort of difficult balance sometimes when we get called into what might seem like a very small project, particularly compared to the HRBT, but it still needs that sort of scientific review. So switching gears, we have taken a little tour from some projects that we were asked to review on behalf of the state. That's not all we do. So I also sit on the executive board of the Coast Guard-led Virginia Area Committee, which plans for and responds to hazardous material spills, often oil. And so this executive board is composed of folks from Coast Guard Sector Virginia, Virginia Department of Environmental Quality, Virginia Department of Environmental Management, NOAA, the US EPA, and us. So you see, we kind of stick out, not just because we don't have a circular logo, but we're the only scientific institution, academic institution involved, which I thoroughly appreciate that they value our scientific input to that planning and response activities. So one of the ways we do that is to, we write the plans and help write the plans and review the plans of what happens if, but then we also exercise them. We have drills, and I refer to it as designing disasters. We make up terrible scenarios that we hope never happen, and we play through them as if they were. So these photos are from an exercise we did on the Eastern Shore in 2019. We set up a full tent city incident command. And then this is me all kitted up in communications gear. Verizon worked with us, and we actually had live stream communications out on one of the barrier islands. The tiny town of Wachapreague, where our Eastern Shore Lab is, had cell phone signal for a single day. They were very happy for that day. And then this is just a graphic showing a trajectory of that spill. So you can see we really kind of walloped the Eastern Shore barrier islands and really made it an awful situation. But again, it was a drill. Some incidents, just quickly in the last couple minutes, that we responded to. So the end of last March, you may remember hearing in the news about the Navy Hawkeye crash just north of Chincoteague Island. So that is out up here. And in this photo, you can see the plane sitting on the bottom. And it's a lovely view across this marsh, part of the Assateague National Wildlife Refuge. So in a sensitive area. And so for this incident, after the search and rescue portion of the incident was complete, then it became a potential spill incident. There was 1,600 gallons of jet fuel on board that aircraft, with clear damage to the aircraft. This is the tail back here. So the first thing we were asked, we stood up an environmental unit that I was part of. And the first thing we think about is what resources are at risk. So clearly we're in shallow water. We're right near a sensitive marsh. And our friend SAV is in the area. So this map is showing the different colors here. Again, blobs. It's really, sometimes it's the best word. So these are just different densities of an SAV bed from 2021. And so in the red dot here is the location of the plane crash. And so we were right on the edge of the beds, and that data is a year out of date with processing time. So it was looking like from the most recent photos we had that had expanded, so maybe the plane was actually in it. And so we were able to provide that information to Incident Command. And once the jet fuel was pumped off the plane successfully without spilling, and we could all sleep that night, the Navy then actually listened and took into account that SAV and changed their salvage plan for the plane to minimize the potential for things scraping along the bottom, both the plane and the recovery barges, and actually worked with us to do that very, very nicely. Another incident that you may recall was the Spirit of Norfolk fire last year. And this was, we also stood up an environmental unit for this response. And the ship here, once all of the passengers, who happened to all be grade school children on field trips, were safely taken off the boat with no injuries, the vessel was towed to a Navy dock where firefighting was able to happen from the water, and that ship burned for 4 days. And so during those 4 days, it was very difficult to try to determine the amount of fuel still on board, if the hull and the tanks were in good shape, if they were cracked, what was going on. We didn't know if it was going to sink. We didn't know what materials might be getting overboard. And so again, looking at resources at risk, we were able to provide data that was actually only a couple weeks old, that we had newly discovered in our trawl surveys, that there were Atlantic sturgeon in the Elizabeth River near this area. And so Atlantic sturgeon are another federally listed species. So probably wasn't a whole lot we could do if they were there during, if something happened, if this spilled or if the vessel sank. But knowing they were there meant that, it was sort of on the list of, well, if this, then we have to make sure we are looking out for them too. So, our advisory world, we never know day to day what phone call I'm going to get, whether it's, hey, could you look at this project with a breakwater and a beach, and I'm not sure if this is going to work well, to, Another phone call might be, well, we just got notified that there's an incident. Be prepared to answer questions about this river. We've got this volume of oil going into the water. So it's never a dull day. So thanks very much for taking this trip with me. We managed to cover 374 miles in about an hour, which I only wish I could get to my site visits that quickly. So I hope you're able to appreciate sort of the breadth of everything that we look at and discuss, and both in subject matter and in area. Everywhere I go isn't even on this map. So with that, I would be happy to take any questions.
Okay, the question is, recent news has talked about mortality in whales related to wind turbine situations and their sonar surveying. Is VIMS involved with that? And what would you do to protect the whales? I don't think bubble curtains will do it.
So we do not study marine mammals here. So I can't give you a direct answer. We do have VIM scientists involved in looking at impacts from offshore wind, but marine mammals is not really is not our expertise.
For Savage Beach, you said that the model did exactly what you wanted it to do, but surely you didn't predict that eddy current forming on that southmost. Well, it didn't never form a envelope. Did you modify the design, or would you have modified the model given the results?
So the breakwaters functioned exactly how they were designed, and we call them terminal breakwaters. You know, the breakwater that's on the end. This was only 3, so sometimes you get long stretches of them. And how the waves refract around that terminal breakwater is very predictable, which is why why Savage Neck was concerned and why they added in that sand at the beginning to see if they could help mitigate that a bit. So it was an expected result of that project being installed. And, you know, if you've seen the breakwaters out here at VIMS or across the river at Yorktown, they are maybe a little bit more of a V than these even. These ones were already a V, and that helps change that refraction point. So that can kind of help mess with it a little bit, but the end ones, you're still always going to have an effect next door.
I was just wondering about the submerged aquatic vegetation and the erosion of the sand and how in the shoreline and dunes and stuff. Is that what you'd call a dependent system of sorts?
I mean, it's all part of one big system. Yes. So SAV, the roots can definitely help hold the sediment on the bed in place a bit. And, you know, therefore, if that sand isn't as mobile, it's going to impact the beach a little bit. But yeah, it's all part of one big system. Did that answer your question?
Yeah. Yes.
Okay.
Thank you.
I'll ask a quick one. How did the beetles fare? For the final conclusion.
There are some folks from Fish and Wildlife here who could probably answer that better than I could. But you know, so the beach locally in the north did get very, very narrow. So that would absolutely decrease the tiger beetle habitat. However, that preserve is much larger than that. And the tombolos that formed in the dune grasses and the beaches there, that actually is also tiger beetle habitat. They used, like one of the permit conditions was that they used the appropriate grain size that the tiger beetles like to live in. So I don't know about.
So they lost a little and gained a little.
Yeah.
Okay.
All right. If you do have any other questions, you can always send them to programs@vims.edu. Otherwise, thank you so much for joining us tonight. And thank you again, Emily.